Okay, so let's examine the relationship here a bit closer. So we've got, say we've got this beam with some sort of distributed load on it. So it's gonna, if we examine a tiny little slice here, zoom in on there, we're gonna see that the distributed load is going to cause some sort of change in the shear. Based upon the based upon the magnitude of that distributed load across that section. So if we take our free body diagram and do the sum of the forces in the y direction, I'll just write that out. Y is equal to, so we've got our V here, and then we've got this minus V plus delta V, so that and then we have the force downward here from that distributed load. So if W is the magnitude of the distributed load, and delta X is the width there, so again, however many newtons per millimeter times however many millimeters, infinitesimal millimeters that we have there, all that is equal to 0. So obviously these V's cancel out, so we can we can essentially solve for this, saying that delta V is equal to W times delta X. So if we want to find how V changes with X, that's basically as X gets really, really small, as we're looking at smaller and smaller slices, the change in the delta V over, so the change in the V over a particular change in X is going to be equal to the negative of the, equal to -1 times the magnitude of the distributed load here. Now again, that's it's negative there because the distributed load is pointed downwards. So if we had a distributed load that was pushing upwards, which you tend not to have too often, but it certainly can happen, then that would be a positive value. So basically what that's saying is that we can find the difference in shear from one point to another by integrating this function over the distance between the 2 points we want. And it's also saying that if we're plotting a shear force diagram, essentially the slope of that shear force diagram, delta V over delta X, is going to be based upon that distributed load. So if we have a distributed load that looks something like this, then essentially we're going to have, the slope is going to the slope's going to be smaller at this point, maximum at this point, start decreasing in slope, so it'll be like, something like that, something similar to that. We can always find out what the slope is by looking at the value of this. So that is, of course, oftentimes a bit more helpful when we have our relatively more easily defined functions for our distributed load. For example, if you have a distributed load that looks like this, then we may end up essentially starting from here and going to here. We're going to be having the shear load, the slope there will initially be 0. So it'll start off at some point. It'll initially be 0. Oh wait, that's the wrong tool there. It'll initially be 0, and then it'll drop. It'll start to decrease until you hit this point here, and then it'll continue to decrease in a linear fashion as long as that distributed load is constant. That's kind of how we determine how to get the slope of our Vx over our Vx diagram. Now, of course, that's for distributed loads. If we have, if we're instead talking about point loads, again, point loads will cause the diagram to jump up or jump down based upon whether or not the load is pushing up or down on the diagram. If it's pushing up on the object, it jumps up. If it pushes down on the object, it jumps down. So we're also worried about the the balance of the moments, how the moments change over time. So again, we have our little free body diagram here, and we're going to be taking a moment about point C prime here, about this corner here. So just adding up the moments that are there. Again, we've got this one here. We got that positive moment there. Got this one here. Again, that'll be a that'll be a clockwise, so that'll be a negative. I got V crossed with the delta x, and again that's a negative because from here to here that'll cause rotation about that axis. And then we are also going to have the distributed load, the force caused by the distributed load. So the magnitude of that is going to be W delta x. And then the moment arm, so of that, the distance over which it acts, is going to be delta x over 2. And again, from here to here, that's going to be counterclockwise rotation, so that'll be positive. That one will be positive. So essentially, as we if we want to find out how the moment changes with time, essentially we're going to take this delta m, divide by delta x. So again, rearranging this equation, these things cancel out. So then we're left with delta m. We want to divide by delta x. We divide these other things by delta x. So moving these two over to the other side of the equation. Moving these terms over to the other side of the equation, we get v delta x minus w delta x over 2. Divide both by delta x over 2, and we get our v minus 1/2 w delta x. And if we're worried about not a large chunk the object, but a really, really tiny slice, then we're going to be taking the limit of as delta x approaches 0. So as that approaches 0, that cancels out, and we're left with just v. So if we want to be, so the slope of the moment diagram is always going to be equal to the shear. And likewise, we can always find the change in moment from one point to another by integrating by integrating our v delta x, by integrating our shear diagram from those 2 points. So kind of a few things that we can look at. So just based upon what we know of how distributed loads work, if we have just a uniform distributed load over an entire beam, then the reactions at A are going to be equal. There's a vertical reaction, obviously. So it'll be WL over 2. And then we can figure out what the shear load is at any particular point by starting by essentially starting with the shear load that we know at would occur at the reaction, and then finding the difference. So essentially, the load at any point is going to be based upon the load at A, the internal shear at A times our Wx. So, and then load at A is just load at A. A is just coming from this equation here, so it gets plugged into there, and then that can be solved for as a function of just the load and x and over L. Then of course from there we've got our shear diagram, so we can find what our bending moment is. So the key here is that the bending moment at the ends, at any free end, is going to be 0. So that's kind of your boundary condition. And then you can integrate, you can just integrate that and find out, we'll get this relationship here. So again, like I said, the slope of your moment diagram is equal to the magnitude of the shear diagram at that point. So here we're starting with a larger positive slope, and then as we get close to the center, the slope drops off, hits a minimum, it flattens out, hits a minimum magnitude, and then starts to drop, and then continues dropping faster and faster until you hit the end, until this slope here is equal to this amount, and this slope here again is equal to this amount. So you can always, you can, if you know what your shear is, then you can find what your moment diagram is by integrating. So let's do an example here. So we got this this sucker here. So what I'm going to do here is I'm going to start from A and work my way back to C, just based upon the principles that we talked about. So basically, at this free end, we know a couple things about this free end. We know initially there is no shear reaction. There's no reaction there, so there's going to be zero shear at that end until it's going to start developing due to this distributed load, but it's not going to be at that point it's going to be zero. Same thing for its moment. At the free end of a beam, or at a pinned end of a beam, there is no chance to develop any moment, any internal moment, so that is zero at that point as well. So I'm just gonna start with a shear diagram. So we know that these forces are pushing downwards, right? So that is a negative distributed load. So that is going to cause the magnitude of the internal shear to decrease from that point. It's going to start off doing so at a rate based upon this magnitude here, and then that rate change is going to drop off until we hit this point here. So I'm going to say draw that there. Something like that. It's not necessarily going to look exactly like that, but if you're just sketching something out, it doesn't need to be perfect. So as for the magnitude of that shear load, that is going to be based upon the area of this section here. So again, we get the change in the shear by integrating the distributed load over the area, over the span of which the distributed load has. So basically, if we've got a relatively simple shape like a triangle, then we can just find that the magnitude of the change in the shear is going to be equal to, that's going to be, area of the triangle is going to be base times height over 2. So that is going to be the value of the shear at that point. Negative because it's pushing downwards. So that's how that changes, how the shear diagram changes between A and B, and then from B to C. Let's just continue drawing that out. Then from B to C, it's just going to be constant. And then at the very end, we're going to have a reaction. We're going to have a reaction at C. And the magnitude of that reaction is going to be equal to the resultant of this distributed load. So that point load at the reaction, because it's pushing upwards on the beam, is going to cause that shear to increase by this amount. So we're going to start at 0 at one end, we're going to increase, and then we're going to get back to 0. You always get back to 0. And that's how we have our shear diagram. So that's V of x. Next up, well, let's figure out what we're going to see for our moment diagram. So for our moment diagram, we know that at this end, it's going to be 0. and it's going to be decreasing all the way until it gets to here. So how we can go about doing that? First off, I think that probably the easiest way to do would be to figure out kind of what the moment is at this point, and then work our way backwards. So the moment at that point, that is just going to be equal to that's going to be a function of how much this is times the distance from here to wherever that thing acts. So we're not given the distance between B and C, but we've got L and we've got A. So we know that the resultant for that triangle, it's going to be acting from this end, A over 3. Whereas if we're measuring it from this end, it'd be 2/3 A. So the moment arm from C to wherever that thing acts, that's going to be L minus A over 3. So based upon that, the moment that this force causes when taken about point C is going to be equal to W naught times A over 2 times L minus A over 3. So that's going to be what that is, and that's going to be a positive moment, right? Because again, when taken about this point, it's counterclockwise, so we're talking positive. So that means that we're also going to have a reaction at C. So I'm going to call that MC. So if we just take the sum of our moments, taken at C is equal to 0. That's 0 is equal to W naught times A over 2, L minus A over 3, plus MC. And therefore MC is just going to be equal to minus that. So that means that if we take a tiny little slice just to the left of C there, that means that essentially the reaction is going to be imposing a moment of MC there, and then immediately to the left of this, we're also going to get, the same amount just counteracting. So that is going to be a negative moment, because we use the sign convention that a negative internal moment is a type of bending which would cause something to turn into a frowny face. Whereas if we had a positive internal moment, that would cause this thing to turn into a smiley face. So when we're graphing that, what we have to do is we have this negative value for the internal moment. That's a bit too far to. That is not even close to vertical. There we go. So the magnitude of this is going to be that. And then between B and C, what we're going to do is we're going to have a constant slope. So we can just draw a line between here and here, and that'll show us the variation between here and here. So essentially, the change in the moment from this point to this point, so this delta m, that is just going to be equal to the area of your shear, the area under or above the curve, the area between the curve and the and the x-axis on your shear diagram. So again, since this is below the x-axis here, this will be, if we take this area here, that'll be a negative amount. So this drops from here to here. We have a decrease in our shear, and it's a linear relationship between there and there. The slope of this line is equal to the amount of this constant shear. Then essentially, once we get past that point, it's going to start varying. So it's the magnitude of the shear drops off. So the magnitude of the shear drops off. So the magnitude of the slope drops off. So once we get to this point, it's going to start looking more like this. So again, at this point here, the slope's going to be 0, and then it's going to be gradually increasing until you get to until it hits its maximum at point B here. And so again, the difference between the value of the raised a bit too much. Never mind. So the difference between the magnitude of your moment here and the magnitude of your moment here, that's just based upon this area here. So that's basically it for that diagram. So I would like to point out that I would like to reiterate that when we have point shear loads, the change in the graph of the shear depends upon the directionality of the of the load in question. Wait, I don't want a box there. I want to. There we go. So let's say we have just a relatively simple support. This is P, so this will be P over 2. This will be P over 2. Again, when we have a point load that's pushing upwards, it increases the shear at that point. So that includes at the reaction. At any reaction. It includes at the end of the beam. So we're starting off at 0. 0 is always our start point. We go up when the point load pushes upwards. We stay constant until we hit where that load's attached. We go down P, we move over, and then we go up P over 2. So up P over 2, down P, up P over 2. So we start at 0, and we should get back to 0. If you end up not getting back to 0 when you get to the end of their beam, then you screwed up somewhere. As for kind of how a point moment is going to affect things, So if we start off with just this beam that's simply supported here, and we apply a positive moment in the center here, what that's going to do is it's going to cause that center to want to twist like this. And if we want that to occur, I'm just going to draw the deformed shape here, generally exaggerated, of course, depending upon how stiff your beam is and how big the magnitude is. But we're going to get a deformed shape. It needs to bend back down here, and this one needs to bend back like this. So essentially what we're saying, and we go back to our definitions of what a positive internal moment is and what a negative internal moment is, we're saying is that we start out on this side of the graph with our moments being all positive, because again, this is a smiley face on this end, and then it switches over here. Once we hit the center point, it switches over to starting to curve downwards. So positive on this end, negative on this end. So essentially what that means is that if we graph how our moment changes when we apply a positive moment in the middle, it causes a drop. So it causes a drop in, actually here, I'll just one second. I'm not going to erase these supports. This is just a graph. So our moment is a function of x. So at that point, we're dropping down due to the fact that we had this positive moment. And then any variation that occurs in the rest of the beam is just going to be based upon the shear load in the beam. So there is going to be some sort of shear load carried by the beam, because again, the reactions will have to be pushing up and down in order to counteract this moment. So we're going to get some sort of linear variation at this point to get us back to zero. So if we have just a moment in the center, that's what our moment diagram looks like. And our shear diagram is just a constant amount all the way across. In this instance, it would be a positive constant amount, because again, the slope is positive throughout. Again, you don't take these discontinuities into account when you worry about the slope. The slope of the moment diagram is still just based upon the shear, and then any discontinuities causes jumps up and down.